cloud. 4 steps for precipitation to happen. First step is we need to cool moist air to dew point. All right, so the air has to cool. Step 2, the moist air needs to condense, so the water needs to condense out. Condensation. Step 3, we need droplet formation. And growth. So droplets need to form. You can have condensation, but if there isn't a way for those droplets to form, you're just not going to get big enough droplets that'll ever fall out of a cloud. And then finally 4, you need to import more water vapor. So a cloud has so much water vapor in it, right? And it can condense out. But really for a rainstorm to happen, you need more and more and more water vapor to come from the outside for it to be self-sustaining, for you to actually have a rainstorm that lasts for more than 5 seconds like we get here in the desert these days. Okay, so let's get some fundamentals here. And this is kind of some fundamentals of water chemistry, water properties. So what are 2 kinds of energy that water can have? Well, I'll give you one, it's potential. What's another type of energy that water could have? You could think of water moving, you could think of water molecules moving. Kinetic energy. So we could have the macroscopic kinetic energy, right, which would be, water falling or moving, right? But we'd also have the microscopic, which would be water molecules moving, vibrating, whatever is going on at that atomic level. So potential energy is obviously related to the elevation of the water. So for high in the sky, we have some potential energy. But we also have some potential energy in the intermolecular bonds. It's the bonds between the molecules, not the bonds within the molecules necessarily. And so say this is our water molecule. O is going to be negative, H is going to be positive. And all of these molecules are kind of have these electrostatic bonds between them, just based on the polarity of water. And water's polar, meaning it has a positive side and a negative side to the molecule. That's why it's such a great solvent. It does a really good job at kind of breaking apart the intermolecular bonds with other types of things that it might dissolve. And so this kind of at this atomic molecular level, we have energy and processes happening that influence how water evaporates, condenses, how it behaves in our atmosphere. And so we'll define another term called vapor pressure. Which we'll denote as little e. And vapor pressure is defined as the partial pressure of water vapor in our atmosphere. So if we write down the total pressure in our atmosphere, that's going to be equal to the pressure from the air, which we'll just say, I guess we'll call this dry air, plus the pressure of our water vapor. So dry air would be oxygen, carbon dioxide, nitrogen, etc. So all these gases are exhibiting a pressure, right? And we have this mixture of gases in our air. So the partial pressure or vapor pressure is the component of water vapor that creates the total pressure in our air. Okay, so we'll call this water vapor pressure as E. This is our partial vapor pressure. Then we have saturated vapor pressure. Can anyone define that for me?
Vapor pressure,
I can't take it anymore. So let's look at Edgar's water bottle right here. All right, so say it's been sitting there for a few hours. It's got this temperature, whatever it is in here, 75 degrees. So right above the surface of that, you have this kind of pressure of water vapor, just the energy of that water. Those molecules are going to be jumping out into the air. And so there's humidity in there, right? There's water vapor sitting in that little interstitial space above the liquid in there. And if it's had enough time and the temperature hasn't changed, then we will reach saturation conditions, meaning it's just going to you're going to have this equilibrium, right? And so there's as much water vapor in that bottle as the air can handle. So if he opens it up and breathes that in, he's going, oh, that's kind of some nice moist air, right? It's going to feel nice on your sinuses. So you've reached saturated conditions. And so we're going to denote that as E star and define it as the maximum potential vapor pressure, E, that the atmosphere can hold at a given temperature. And so we've got a relationship that is driven by temperature. So we'll say temperature degrees Celsius. And you've got this curve that kind of looks like this. And right here, we've got 0 degrees Celsius. And this is our saturated vapor pressure in pascals or some pressure unit. And so you can see it's nonlinear. And so when we're above, there is a vapor pressure. Ice has a vapor pressure. But when you get above that, you've got this nonlinear relationship. And kind of in this zone right here, you're getting about 6% more vapor pressure per degree Celsius. And so it kind of, increases at this rate. So even ice has vapor pressure. All right. And this is why we talked about, when we talked about storm attribution for climate change. Well, can we say a particular Hurricane Laura right now, it's bashing Louisiana. Oh, well, we have more hurricanes because of climate change. Maybe we do. But for a given hurricane, if it's a little bit hotter than it normally would be in a given year or a given season or during this particular hurricane, well, that hurricane is going to be able to have more water vapor available to it from the ocean, for example. Because if the air is a little bit hotter, now we can have more water vapor in the air because it's hotter. So then we might have more rain, right? And we talked about that study where they modeled, what was the hurricane that hit Houston? I'm not gonna remember now, but Harvey hit Houston. Yeah. I knew it was an H, but it didn't make sense for some reason. They said, I think they said it was about 10% or 12% more rainfall came out of that hurricane based on the average increase in temperature from the 80s that we've experienced. So that was their finding there. Okay, so we have, yeah.
Just a quick question for clarity on that. The 6% more heat per degree Celsius. So are we talking about something that's contained still, or are we talking about like just the atmospheric pressure out here? Like if I look at that, like, I mean, I feel like if the temperature is 100 degrees here, the thickness of the air here, why don't we have more vapor pressure?
Okay.
Like down south.
Okay. So this is a theoretical thing, right? This is the potential, maximum potential. So if you don't have water to put in the air, you're going to have some dry air. Right. So down south, you've got water. You have more water vapor just coming in from the atmosphere, from the surrounding oceans and seas and everything like that. You have more water in the ground that can be evaporated. So you just have a bigger source of available water to go into the air. If Grand Junction all of a sudden got a massive lake right here or something like that, then yeah, we would have humidity, but we don't have that water source. So they have
a higher potential in vapor pressure because they have more water surrounding them.
For a given temperature, and it doesn't matter. So it's 100 degrees here, it's 100 degrees down in Miami. The E star is going to be the same everywhere because it's just a relationship of temperature. Okay, so that's the maximum potential water vapor you could have. And then what you actually have, so this is a great segue, we're going to talk about relative humidity. Okay, so relative humidity is defined as, we'll do it, RH is defined as the vapor pressure over the saturated vapor pressure. And so it's a percent. And basically we just get, right now in Grand Junction, the relative humidity is, I don't know, 20%, something like that. Down in Miami, it's 90%. It's the same temperature, but the actual water vapor in the atmosphere is much less here versus there. And that just comes from, okay, well, where's it coming from? It's got to come from some water body typically. And so down in the south, they've just got, because of their climate and the jet stream, they've got more water vapor in the atmosphere. Because we're sitting in the middle of the country on the leeward side of all these mountains to the west of us, we don't have all that moisture.
So that relative humidity is just like how much, like percent that we have compared to
what we could have.
What we could have. Okay.
Yeah. So if you think of the atmosphere as a sponge, and when you have a really high temperature, your E star is really high, and that sponge is really dry. The sponge can only hold so much water based on the pore space, right? So it's basically where are you starting out? And so the relative humidity is kind of, you can think of it as the saturation of the soil. We'll talk about that. What's the water content of your soil? Well, the pore space is the maximum amount of water you could have in it. And then the moisture content, or whatever the term is, I don't teach geotech. I just married someone who does. That would be like the relative humidity. How much is that soil or sponge filled up, percentage-wise? All right, and then one more term that we've got here is dew point. Does anyone know what dew point is? You probably heard that word.
So the temperature on which vapor becomes water.
Yes, exactly. So say we've got this water vapor in the atmosphere. Dew point is the temperature. So it's an actual temperature. So it's the point, and we'll call it T dew point. It's a function of water vapor, the water vapor content in the atmosphere. So it's the temperature at which, or sorry, to which the temperature to which we would need to cool a parcel of air to reach E star, the saturated vapor pressure. And then once we get there, that's when condensation spontaneously occurs. All right, so say our, here's E star, but we could also say, you know, E, it could be E. Let me just do this in a different color. Okay, so we'll have E. So E is gonna be, we'll just say our E is a certain thing. So here's our temperature and our E is right here. Okay. And so the idea of this dew point is given our E, how far do we have to go to hit that E star? And so this is going to be our TDP, our dew point temperature. Okay, so when you hear the dew point is 50 degrees, that means we'd have to cool down to 50 degrees for your grass to start getting dew on it. And that, you know, that usually happens. If it's 20 degrees, or I don't know if that makes sense. If it's 40 degrees, well, there's a lot less water vapor in the atmosphere, right? And so it's got to cool a lot more so that we get to that saturation point. Okay, let's go back to our 4 steps of precipitation. Let's do black. I was trying to get PowerPoint to work because when you draw on PowerPoint, it looks better. It like does this nice smooth kind of, it looks like an actual pen. I don't like this choppiness, but maybe I'll figure it out one of these days. Okay, so who remembers what the first step of precipitation formation was? Cooling. How do we cool moist air? Or just how does air cool in general?
By rising.
Rising, thermals. Okay, so these are all great things. So what's a thermal? What does that mean to you?
I mean, I think of thermals as the wind direction and heat either rising or dropping.
Yeah. So
Well, not dropping, but it cools and it drops.
yeah. So air. So we could say hot air rising. What's that process called? Convection. So convection is heat causing a movement, right? And it could mix. We could have radiation. Remember we talked about that black body radiation. So anything that has a temperature emits electromagnetic radiation. Typically in the temperature range that exists on our planet, what form is that electromagnetic radiation, Val? What's the wavelength or what's the kind of radiation that things emit? I'll give you a hint, we can't see it. So we'll be on the other end of the visual spectrum. Ultraviolet is going to be you know, a shorter wavelength, higher energy state than visible light. So what's the other one? It's how we feel heat from the sun. So infrared radiation. And then we could also have conduction, which is simply that contact transferring energy with land. So these are all things that can happen. But let's talk about, so all of these guys right here, and I'll say this mixing. So these all help with condensation, but really we need just this kind of massive lift of air. And so we'll just say air rising, and there's a lot of mechanisms for this. So let's talk about this adiabatic process. Does anyone remember what this term means? What's that? A little hint.
There's no heat loss to your surroundings.
No heat lost. So adiabatic means energy is not lost or gained. So an adiabatic process is a process where energy is not lost or gained. And so in a system or control volume, so when we have vertical uplift occurring, if it happens kind of fast enough, an air parcel moves up. And if it happens fast enough, we're not changing the energy. And so if we don't change the energy content of a parcel of air as it goes up, what happens? So let's think about the pressure here and then the pressure up here as we go up in elevation. What's happening to the pressure as we go up in elevation? Pressure's increasing? It's decreasing because it's harder to breathe up there. The air is thinner, right? Okay, so if the pressure decreases, then this parcel of air is going to expand, right? Because there's less pressure on it. And then what happens when a gas expands? By the, I don't know my thermo, and I should have this written down, but there's a law there, right? Ideal gas law. P equals V and RT. And so pressure goes down. We're going to say volume goes up. And additionally, the temperature will go down to account for that. So as it expands, it cools. And we know this because you know, when you're cooking on that gas grill and you got it cranked up, all 4 burners going, you feel that gas tank, it's cool, right? Because the gas in there is expanding as it's coming out. If you ever fill a gas tank, it gets hot because it's compressing. So as we get this vertical uplift, we have an adiabatic process. The gas expands and then it cools. All right. Or if you feel your bike pump tube, you know, you're putting air into your bike tire and you feel that tube, that's going to be hot because you're compressing the air. Okay, who remembers the second step? Condensation. So we have that cooling, right? And we cool to the dew point. And now we have condensation at that dew point. So once you have that condensation, you've got liquid water, But these are like molecular droplets, right? These are teeny tiny liquid water droplets at the molecular level. And we need about 10 to the 8 molecules to collide and form a stable water droplet. Meaning it's not going to kind of go in and out of gas and liquid state. Okay, so this is not going to happen on its own. From a probabilistic standpoint, just you've got all this air, you've got these teeny tiny molecules, and for what is that, 10 million of them to collide at once, or 100 million of them to collide, it's just not going to happen from a probabilistic standpoint. It would take too long. We're never going to get a water droplet. So what do we need from there to actually get a stable water droplet?
Need like nucleation sites.
Yeah, we need some nucleation site. We need a catalyst. And so we need what's called condensation nuclei.
Step 3.
What's that?
This is step 3.
Yeah, this is step 3. So condensation nuclei. The idea is, I mean, this could be anything: aerosols, smoke, dust, particles. The atmosphere has got a lot of junk in it. And sometimes we need that junk for rain to form. And this is the concept of, so this could be dust, this could be ice crystals, smoke. There's stuff in the atmosphere. And so condensation nuclei leads to ultimately, which is the true step, which is droplet formation and growth. And you get this idea of, as you get these water droplets and they kind of grow bigger and they fall, they get bigger and bigger. As they get bigger, the bigger droplets are falling faster than the smaller droplets because they're heavier, so they just fall faster, right? And so as they go, they're going to bump into these guys and get them and grow and add them to their droplet size. So bigger droplets are falling faster than smaller droplets and kind of growing as they fall. Okay, so once you've got this droplet formation and you have condensation happening, you kind of get this positive feedback cycle. So condensation releases heat, right? That was in the quiz. Condensation releases heat. And the way to remember that condensation releases heat from the water is we know from experience that when our sweat evaporates from our skin, what happens to our skin? It cools, all right? That's the whole cooling mechanism that our body has. And the reason it cools is that when water goes from liquid to gas, it's entering a higher energy state. To enter that higher energy state, the water absorbs heat from the environment and takes that heat with it. So water vapor actually has a lot of energy stored in it. When it condenses, it releases that energy, it releases that heat into the cloud. What happens when you release heat into a cloud? You get more air coming up, right? So hotter air is going to rise. And you kind of get this uplift that happens within the cloud.
So that hot air rising out, plus these droplets are getting off heat.
So you think of like a thunderstorm, right? Afternoon thunderstorm.
Right?
What's that?
It cools up there, right? In the clouds?
So when the air rises, it's expanding and cooling, which gets you to condensation. But once you get condensation, you're releasing heat. So you're actually warming, but you've already started that condensation process. And so now that you're releasing heat, you're causing more air to rise and then cool and condense. So that's the positive feedback cycle. Does that make sense?
Yeah.
It's a little, yeah, there's a lot of steps there. Okay, so more uplift, and then more uplift yields to more condensation. And then the last part of this, once you've got this nice kind of storm cell going, is you need to import more water. So the last step is a rain cloud, we'll call it. All right, so just kind of some basic statistics. So a large thunderstorm might have about 1 centimeter of water in it. So just look at a given cloud. That cloud, given all the water vapor in it, if it were to fall out all at once and be reduced to water, it'd be about 1 centimeter of water. So that's like a big kind of storm cloud. So obviously we get rainstorms that drop more than 1 centimeter of water, not necessarily over one spot, but as they move, they're going to drop out more than 1 centimeter of water. And so so that means that we have to recruit water from the atmosphere in order for that storm to last and to actually, so let's just kind of draw our storm cloud here. So something caused this to rise. So we'll just say maybe we had a really hot day and we had some water vapor and then that air rose and condensed. So what's happening within that cloud is that you've got this condensation occurring, right? No droplets are falling down. As they condense, they're causing warm air to rise. And then as it rises, it cools and gets more condensation, which comes down. So you kind of get this growing, that's why clouds are kind of growing, right? They're really tall because of that. So while that's happening, we're getting rain. Raindrops are falling down on our heads, but then we're also sucking in more water vapor from outside.
When does it stop and grow in terms of like height? So.
Yeah. So you reach, you'll see, for example, so this kind of cloud, maybe it gets so high, it starts to kind of stretch out because you get different velocities of air, air masses. And so maybe you enter, I don't know the different names of the atmosphere, I'm not going to be able to tell you off the top of my head. You could also reach a point where it just gets so cold up here that the process kind of gets shut down. So there's limits, and that's a little more advanced than my knowledge to what happens. So it's not going to keep growing indefinitely into space. Okay. All right, so let's my screen. Okay, here's just a little, do we have a video here? We do have a video. Okay, we have a video on cloud seeding. Let's check this out.
Spread across Colorado's high country hills, machines like this are planting snow seeds in the clouds.
Cloud seeding does not create new weather, but it's a way to work with the weather passing through Colorado and get a little more snow from every event.
Snow is critical to Colorado. It's the
So I should introduce this. We're talking about cloud seeding, which until recently was thought to work, but we didn't actually have solid proof. And actually in this last year, we got some definitive studies that cloud seeding does work. And the idea of cloud seeding is that third step in the process, which is introducing more condensation nuclei into the atmosphere. So they're basically injecting fine particles into the atmosphere to encourage more precipitation to happen.
Primary source of our state's water supply. That's why the state of Colorado, the Colorado River District, 3 ski areas, and the Front Range Water Council, including Denver Water, help fund the Central Colorado Mountains River Basin Cloud Seeding Program.
This is silver iodide. This is what we use for cloud seeding. It's a naturally forming element. So this is
Silver iodide.
And sprayed over a propane flame.
The program uses 2 high-elevation, remotely operated generators and more than 20 manually operated machines.
So we pressurize our tank. And we carefully light our chimney.
Generators vaporize the silver iodide, and wind lifts the material into the clouds when conditions are right for enhancing snowfall.
Silver iodide adds additional particles to help harvest the atmospheric water. So then you have the 6-sided particle floating along in the cloud, vapor starts to build on it, and when enough is added to that particle, it will turn into a snowflake and fall out.
The program seeds clouds over Eagle, Grand, Pitkin, and Summit counties to boost snowpack in the upper Colorado River Basin. Breckenridge, Keystone, and Winter Park ski areas help fund the program as well to generate extra snow at their resorts.
Over the past 30 years, Winter Park Resort has participated in some type of fast seeding program. When the storm system comes in, we are able to turn on the fast seeding generators and actually bring an additional 1, 2 inches, 3 inches of snowfall. The benefit to the additional snowfall is important for the recreational resources. And it's a benefit to Denver Water because there's an additional amount of water than else in the springtime for water use.
Mountain snowpack provides over 80% of water supply for Denver. So we're always interested in looking at options that could create more snow. Well, it's hard to pinpoint exactly how much snow is produced by cloud seeding. Data suggests that it has been successful. So we continue to work with our partners on the East Slope and the West Slope to invest in cloud seeding. You cannot see every cloud that comes through in Colorado. There's a window of opportunity for cloud seeding. We're trying to catch that part of the storm that's cool enough with a lot of liquid water.
Studies support the benefit of cloud seeding when proper atmospheric conditions exist.
You can get about 5 to 15% more snowpack from good machines burning a high silver rate and a wet storm.
Estimates from Western weather consultants show how small amounts of additional snow over wide areas add up over the course of the winter.
Over the last few seasons, we've estimated that within the CCMRB program that we've been able to produce on average around 60,000 additional acre feet of water for the entire area. There is this kind of rich history of the lure of we can help with the clouds. We don't know everything, but we do know what types of clouds to see, what material we should be using, and that it's not a cure-all, but it's going to add more to the system and be helpful.
All right, Denver Water. So they were talking about some estimates. We think it does this and that. So this video was made before this research came out of CU Boulder. I think it was Atmospheric Sciences. And they use these radar rigs, these trucks with these radar, and they drive them into storms. And they would look at kind of basically they had an experiment. They had a storm that was cloud seeded, and then they had another area that wasn't cloud seeded. And they would compare the amount of precipitation that came out. So they had a really kind of basic design, but sophisticated equipment to actually measure it directly before people had done modeling studies, which just, you know, it's not data. So they were able to prove that cloud seeding does in fact work. And I don't know the exact number because it's going to vary on the storm, but you put more basically platforms or catalysts for condensation in the sky. And if there's enough water vapor in there, you can actually get more snow.
Funny how Vail was in there.
What's that?
I said it was kind of like interesting how Vail Resort was in.
Vail?
Yeah. Was in, like, Convective.
Oh, were they out of it? They weren't part of that? Vale's like,
Yeah, that's like-
they were fine. So there's actually a cloud seeding network on in the Grand Valley, sorry, up on the Grand Mesa that the different water utilities and irrigation companies participate in.
Hey, Joel.
Yeah.
I can't see the PowerPoint right now.
Let's see.
Yeah, I was wondering about that because they had that map on there and they showed different areas that they were participating in.
How about now?
That's good. Thank you.
Yeah, so that was the program that Denver Water is part of, and that was a Denver Water video. So they're going to be focusing on their watersheds where they get their water supply from. But there's other networks, you know, that just weren't featured in that video.
Is it expensive?
I don't know, and maybe we can get someone to talk to us about it, because City of Grand Junction participates in it, and they pay, you know, it's a consortium, right? So all the water users pay into it. I think they pay on the order of $50,000 a year or something like that. Not super expensive, but it takes personnel, it takes equipment.
Then how much is the silver iodine?
Silver iodide.
Iodide.
Hmm.
How much is that?
I don't think it's that expensive. Yeah. All right, so here is a picture of water vapor related to precipitation. So the yellow here, this is a satellite image, is water vapor. And this is water vapor that is coming up from the Pacific Ocean. And what we have here is I think this is a low pressure system. Low pressure systems spin counterclockwise. High pressure spins clockwise. Right now, we've basically got the opposite of this because we've got a high pressure system spinning clockwise, and it's taking all this smoke from California and Colorado and just swirling it around. At least that was happening last week. Okay, here we have the opposite condition, a low pressure front. And what's happening is, and then there's a high pressure front sitting right here. So what this is doing is pulling a ton of water vapor up and around from the Pacific, and it's slamming it right into the Rocky Mountains. And so as that water vapor hits the Rocky Mountains, it falls out as precipitation. And we had those massive flood events. So we'll talk about that, and we'll go to our whiteboard. How did I get to that whiteboard? That's what I thought too. Share whiteboard. Okay. We'll erase that funny little thing. So let's talk quickly about the kind of storm types we have. These are also, you could also think of this as uplift types, ways that we raise moist air. We could have frontal, also known as extratropical cyclones. A cyclone just means spinning, right? It's just spinning air. And low pressure systems, high pressure systems are air that's kind of swirling around. And when you have frontal events, what you have is potentially you could have warm air like this, and then a front is going to be moving cold air over warm air. And so when that happens, if there's moisture in this air, you're going to get clouds starting to form at this front, and then rain happening. So it's when two air masses collide, basically. And if it has to be cold over warm, right? Because well, I don't know. It might work. You could have warm fronts and cold fronts, right? I think they just behave differently. Oh yeah, so cold fronts. Let's look at that real quick. Cold front. You have a cold air mass replacing a warm air mass. This often happens in the wintertime, where maybe things are heating up and you get this cold front move through. You get a bunch of snow and weather, And then kind of behind that, you get clear, sunny. Those are those bluebird snow days, right? You get a powder day, it's snowing, and then it's beautiful outside after that. So the front is this interface where the two meet. These are typically smaller, more intense storm events. And this is because you have a steeper uplift. You got your warm front. And that's going to be warm over cold air. This typically occurs over a larger area, and it's less intense. Okay, so tropical cyclones are another way we get air, and I'm not going to get into those, but they're obviously, these kind of self-sustaining weather systems that suck a bunch of water vapor into them and just create a massive amount of rainfall. So that's what Hurricane Laura is right now over Louisiana. And I'm not going to talk about those because we don't get them here. We can have convective storms. And this comes from surface heating. That's why we get afternoon thunderstorms on the Front Range or monsoon storms in the evenings and afternoons here. So surface heating creates convection, right? And so hot air rises, it cools and condenses, and you get thunderstorms. All right, and then the last and most important one for Colorado is called orographic. Who can tell me what orographic means? Orographic uplift. Christian, what's orographic uplift?
Isn't it like with the mountains and how the mountains pull the air up, the warm air up to the mountains?
Yeah, exactly. So here's GJ sitting down here. Here we've got, I don't know, we'll just call this the Gore range. Maybe is that the first big range that we hit. So you've got your air coming. Let's do a different color, guys. Let's make it interesting. You got your moist air coming. It hits the mountains. It's got to go up. And when it goes up, it cools, and then we get thunderstorms. So you think of the mountain thunderstorms. Those are really common in the afternoon. You also think about the fact that it just snows a lot on the western side of the mountains, more so than the eastern side. That's true over in California with the Sierra Nevadas, the Cascades in Washington. It's true here in Colorado. That's why Denver Water is investing all these resources into cloud seeding in the upper Colorado basin, because they're sucking that water over to the Front Range. So orographic uplift is simply orography, or orographic refers to mountains, or topography. It doesn't have to be a mountain. It could just be a slight rise. There's this thing called the Palmer Divide, which is a slight rise in topography between Denver and Colorado Springs. And they get a ton of thunderstorms there because of the topography there. And it's not a big feature. You know, Highway I-25 goes over, you climb, gradually you come down, but it's enough to make a difference. All right, last thing I will talk about, and we'll kind of look at some pictures, is monsoonal rainfall. So monsoon is a word. It originally came from Arabic and then was kind of updated in Portuguese. And it really just refers to kind of seasonal weather. related to the time of year. So we've got monsoon season. We didn't really have it this year, or maybe we will have it. It's particularly dramatic in Arizona, New Mexico, where they'll get just massive flash flood events that can happen in the late summer, early fall. They've got just really big flooding challenges related to the monsoonal rainfall that happens there. This also happens in India at the foot of the Tibetan Plateau. So you've got this orographic feature, and then southwest US. So let's look at some slides related to that. Okay, so here's India. Here's the topography of India. And you can see that you've got the Tibetan Plateau, which is, this massive, this is where the Himalayas are. So just a massive, you go from basically sea level, 1,000 feet, all the way up to, 15,000 plus, 20,000 feet near Mount Everest is almost 30. And during the summertime, you get the wind bringing moisture across the continent, and they hit these different topographic features. So when they hit the Himalayas, they dump out so much water, so over 1 meter of water. In some places, it's multiple meters of water. And then that just dumps out into these rivers that then flood and kind of wreak havoc. Here's Bangladesh right here. Bangladesh is the confluence, the delta of a number of these rivers. And Bangladesh is basically underwater for certain months of the year because of the monsoon floods that come. It's pretty wild. So this is kind of the biggest monsoonal system that we have. The Southwest US also has this. So this is how it plays out in the Southwest. You've got the Eastern Pacific Ocean down here. And the winds kind of set up in a certain way during summer, late summer, that bring that moisture up into the southwestern US. And so you can kind of see this yellow and orange. These are where the monsoon rains are falling out. So from Arizona, southern Arizona through New Mexico, up the Rio Grande Valley, and then into Colorado. So that moisture is coming from the Pacific Ocean. And in the summertime, it's coming out either in convective storms or orographic storms. Let's look briefly at just kind of what our average annual precipitation looks like. This is the 30-year normal for the country. And you can see that the wettest part of the country is going to be in the Pacific Northwest. This is where we get those temperate rainforests. They get over 160 inches of rain. And then we've got our nice dry regions with these mountains. These mountains are our water tanks. This is where we get our moisture in the west due to snow and due to that orographic effect. Here's what it looks like in Colorado, zooming in a little bit. We've got some really dry areas, the San Luis Valley, the Gunnison and Compaggre valleys, Grand Valley as well. But then we got these really wet areas. So quite a bit of difference in average annual precipitation between these areas. Now this is average annual precipitation, right? This is the climate. Here we have a map of the 100-year, 24-hour rainfall depth. So this is going to be from a particular storm event. And what they've done is they've taken all the rain gauges together and kind of created a smooth map for the whole state. And what this is showing you is where you would have a 24-hour event that's really extreme. So the darker colors, the blue and the cooler colors, the blue and green, are going to be more extreme rain events, and then the lighter colors going to be different. So now we have a different image here. The mountains are no longer the cool colors where we get the most precipitation. Rather, the mountains don't get necessarily extreme precipitation, right? Maybe they'll get a small thunderstorm, but they're not going to have the major flood events that the Front Range sees. And you can see the Front Range and then Eastern Plains is where we get the biggest, most intense thunderstorms. So this is weather, extreme weather. and this is climate.
San Luis Valley has a good aquifer.
Yeah, man, they're struggling. They don't get any rain.
It's hot and they don't get any rain.
They only get that precipitation from these guys and this, and that aquifer is going down, unfortunately. So this is the extreme weather, and then here's the extreme runoff. So these are from USGS gauges, and this is showing you the ratio of the peak flood event in that record on that gauge over the whole decades that it's been running to the average flood event. So if you average all that, you take the biggest one and divide it by the average. So where it's greater than 4, you can see a dot here. And so most of our dots, you can see the gray dots are the gauges across the whole state. And then the colored dots are where you have extreme flood events with this arbitrary ratio or arbitrary threshold of greater than 4. So the most extreme events are happening on the Front Range. They're happening on the Arkansas River and its tributaries. And then we get some extremes out here. These are small, tiny drainages. This is in the Piceance Basin, Piceance Basin. As well as some of the smaller drainage areas, smaller streams can get really intense flood events. Okay, we've reached our time, guys. Thanks for your attention.